I was going to make a response to your video, but it seems you've now taken that down. But I did take a few notes before you did that, just so I could respond to some of the accusations and nonsense that you came up with. I mean, first off, obviously, it's going 4 times the velocity. Major mistake there. Recoil. The recoil wasn't shown. Yes, it was on all of them. Right, he's saying submit it to a journal or peer review. I think I'm probably about 300 years too late for that. You know, it's been known and it is used in the construction of cars, planes, buildings, bridges, machines. You know, it's well evidenced, well documented and true. Hence, it's used regularly. So, as for peer reviewing here, okay. What we got here? Yes, only you could see the faults. Yes. Like I said, in the comments, you will come up with a fatal flaw that only you can see, and as predicted, you did. Clearly, the results do not make sense to you, but regardless of them not making sense, that doesn't mean it isn't true. They were falling at the same speed or something. You said at one point gravity makes them fall at the same speed. No. They accelerate at the same rate when something's falling in gravity, but not the same speed, because acceleration is not speed, is it? And then it was rather bizarre because you mentioned yardstick. You could have used the yardstick if you'd actually bothered to watch the previous video. That's exactly what I did. Then you mentioned the recoil again, saying how important that could be to be seen, which it was. And what have we got here? Oh yes, you should use the raw camera footage. Yes, I did. I even stated that quite clearly. So it seems like you just picked up on things I stated and worked them into your video, because you didn't really have a lot to say, did you? There was no editing of the videos, like I say, they were raw. Then you strawmanned about telling the truth, which I was actually talking about you. You know, I said it's never been about the truth. I was pertaining to you, not myself. Then you went off topic quite a bit, going on to editing experiments and all that kind of thing, as usual. I think in there somewhere you mentioned something about I've said enough and it'll be on my epitaph, so I don't know if that was a cowardly, you know, veiled death threat there because you didn't like the results. Then you whiteboard doodled again, because obviously physical evidence, you know, that doesn't matter, you can just draw it on a board. And then it's unreasonable to think that. Well, to you it is. And then it didn't and can't and won't ever happen. But it does, doesn't it? That's the thing, it does. I mean, this is basically what you want to do. You're angry with the world and everything in it. Oh, there we go. Kaboom. Well, that's the thing, you're calling everybody fakers and liars, and it wasn't fake, was it? It was honestly and openly presented to you in the best way possible. And like I say, it's never been evidence. I mean, I think I look back into, to say Leibniz never did it. From what I remember, his experiment was actually using a ramp and a pendulum at the bottom and he rolled masses down to hit the pendulum to see how much it displaced the pendulum. And when he did it with a £1 and a £4 at the respective heights, the displacement of the pendulum was the same. So to say he never did any experiment, how do you think he come up with the conclusion? He obviously theorised it and then he tested it. To say it's never been tested in the history of humanity. Of course it has. I say it's used every day in industry, in design, in machines, in to say it's not a thing and it's not evidenced. Anyway, it seems you made some sort of apology or retraction. Well, I'll say apology. That'll probably be on you. But some sort of retraction video. So I shall probably do a response to that. So before I get into this, I'd just like to say a massive thank you to everybody who showed genuine support. Obviously a massive thank you to Dispar for his analysis, showing that it's almost exactly twice the speed. I mean, we're talking 0.1, so in terms, all experiments have some margin of error, and it's a very low margin of error. That's been proven to you. You've obviously watched it. I'm sure you've received emails as well. I think Lasker said he was going to email you. So you've obviously changed your mind now in light of finding, some new information out, not just jumping onto it and doing a leaks like seems like, you have to analyse these things. Right, so here we go. Let's have a listen to this.
Time for DraftPhysics.com video presentation, a retraction video of sorts. I'm going to delist.
Bit of a nervous cough there.
A previous video I made where I asserted that these velocities were wrong based on how I viewed an experiment. But I'm still a complete asshole. It's still a fake piece of crap, blah, blah, blah. But
right, the arsehole thing, couldn't give a shit about, but fake.
Was wrong, okay, to present it the way I did in terms of this.
Produced this piece of crap video.
Yeah, this.
It's got great frame rates.
Okay, so the actual video doesn't demonstrate what I claim in the sense it does demonstrate the velocities don't match, but I didn't consider the fact that both.
Right, it does demonstrate the velocities don't match. That's because obviously you've watched Dispar's video and they don't match by 0.1.
Objects are accelerating at a different rate. One object is only falling 1 unit of distance, the other one is 4 units of distance. So one object has got its much higher velocity than the other one because it hasn't fallen as far. So you really, because they're gaining velocity, they're increasing their velocity every.
They're gaining velocity. What they're doing is, it's called accelerating. Acceleration's a thing.
Bit they move, they go faster and faster. You really have to get just average velocities, and I was really getting an unfair average, so that would be the right way to say it. It's
He's obviously got one of these
unfair. Okay.
What I did.
Cameras that does this really nice. See how nice that is. I mean, it's really nice. All right. Instead, he did this fake experiment.
So it's still a garbage experiment. Okay, so we'll go over other.
Right. So it was fake. Now it's garbage.
Reasons why it's a piece of shit. So yes, I only needed the one reason when I thought the velocities were way off. Now the velocities, in my opinion, are still off, but it doesn't. They're not off as dramatically as I claimed. And
no, not anywhere near dramatic, is it really?
And so I guess I'll have to put the images in here. So I guess I will do that. I'll take a pause. All right. Unfortunately, this image isn't quite as good as I ended up with this little crap. The 0 zeros in there. But if you look at the two images, what you might seem obvious to you is that somehow this spring looks like there's a lot more spring showing than this spring. So the spring on the left, there seems to be less spring showing, obviously indicating it's more compressed. And yet the two needle.
Yes, this one is more compressed than this one. If you'd been following along, that's exactly how it should come out. how it was predicted to come out. So all you're doing here is confirming the prediction.
Let's read the exact same reading. So it's the exact same reading, but there's clearly the one on the right looks much...
Right, they're not exactly the same, because if you look at the 3 and the 3, you can see more of the 3 on this one than you can on this one. There's no point looking in the background, because obviously that's further away. It's a different perspective, you know, you want to get the thing closest to, you know, and as, you know, all you're doing here is illustrating that you haven't followed along at all.
Bigger than the one on the left. And so I have another image that illustrates that. All right, so here it is with a ruler, and so you can...
And yes, again, you're showing there that this one is compressing slightly more, roughly about a mil, as predicted.
This sort of gives you the indication that there's, if you look at the one on the right, that the needle isn't really pointing straight, it's pointing in this kind of weird angle, and that there's...
As I've said, this needle, you know, obviously it's not a needle, it's a zip tie, you know, but I've no need for it now, so we can actually, you know, drop the masses and see the edge of the mass itself. So yes, these aren't ideal, but using the frame rates I previously used, I needed some marker. Now I don't.
More space. Now the thing that really gives it away is that the pink part. So if you look at the pink part and where...
And again, you're picking something way in the background.
It covers, well, the ruler sort of tells you it's not a straight line. So if you look at the line of the ruler, it cuts across a different portion of the...
It's about a mil difference,
zip tie.
exactly
so
as predicted.
On the left-hand side, the ruler goes over the zip tie. On the right-hand side, the ruler is below the zip tie, indicating the weights aren't at the same heights. All right.
No, the weights aren't at the same heights. This one's from 4 heights and this one's from 1 height. That's the whole point of the experiment. And just to remember here, this is 1, this is 4. This has twice the momentum of this one.
So I have another image.
Oh.
All right, so this is probably the best of the images. Let me move it so you can see the basis. That's the important part. So you can see that nothing lines up. The little zeros aren't lined up.
That up a bit. I don't know what you're doing there, but
little white, the clear zero is clearly over the pink, not over the pink. The 1 is further down on the left side than on the right side. You can see the number 2.
Not a very good analysis.
You can't see the number 2 on the left side, indicating that yes, one spring.
And like I say, if you've been following along, this is perfectly in line with what I've showed and measured and everything.
Is much more compressed. Now, let's understand it's at least 2 or 3 millimeters, and the entire compression of the spring, because you used a really stiff spring, the spring's entire compression in the experiment.
Again, the reason I've used a stiff spring was explained.
It's only a centimeter, so 3 millimeters is huge when you're considering that you're talking about only 10 millimeters of total compression. So it's really way off. Considering. So he should have used a softer spring. I mean,
it's not way off, it's about a mil off, and I should have used a softer spring. I have used a softer spring, and you didn't accept those results either. This was to try and make it clearer, you know, because when I do it with a softer spring, you have to take a number and subtract it from another number, and that seems difficult for you, subtraction. So I thought I'd try and make it simpler and more visual for you.
Such a stiff spring means that you're trying to do all of this detail in a tiny amount of space. So if you used a spring that would have compressed 5 or 6 centimeters, it would, all of these little details wouldn't have mattered. But the little details matter when you're...
The thing with using softer spring is you have to do a lot, like I say, you have to faff about a bit. It's not quite as visual.
Using, you know, a spring with such a high compression, such a stiff spring. So it's clearly...
It's not a particularly stiff spring, it's just stiffer than the previous one I used. You know, you can compress it quite easily. You've got to remember, these masses, that's 20, less than 25 grams, and this is less than 100 grams. We're not using, this is not 1 pound, this is not 4 pound. They represent that, but they are not those weights. It's 25 grams and 100 grams.
Reading exactly the same number, and yet clearly one spring is more compressed than the other. Just a fact.
Yes, it is a fact, and it's as predicted. If you'd followed along looked at all the measurements, looked at all the setup, you would understand why this one is a little bit more compressed, and we're talking a little bit, aren't we?
So it's still a junk experiment. Still garbage. It's just garbage for a different...
So it's junk and garbage. It's not fake now, though.
...reason. So the fact is, I claimed that the one mass was going a little bit faster, and on top of that,
wait.
zip...
A little bit faster. No, twice as fast, you said. And actually, to go that speed, I would have had to drop it from roughly about 1.68 meters if I'd have wanted it to go 4 times as fast. So I'd have probably had to drill a hole in my ceiling.
Tie is in the wrong position on both of them. It's not at the same place on both of them. One's a little lower and it's a little higher on the other one. And so it's deceiving you based on what the real distance is. Of the action.
And again, you're missing the point. One of them is a 1 mass, one of them is a 4 mass. They are almost compressed exactly the same. This one has twice the momentum of this one.
Compression of the spring. So, real crap experiment. So we'll just go over some of the stuff that was in the other video. Maybe I'll just play the end of the video and just add this bit. So maybe I'll do that and save myself some talking, some extra talking.
Mm-hmm.
So we'll get rid of this. And I'll show, I mean, this is, it's not much math, but it's sort of important. And you really can't see that very well. Actually, if I can highlight it in some way.
Dear.
Yeah, that would be better if it came out a little brighter. All right, so this is just 2 comparisons here. So this is the 1 pound comparison. This is the 4 pounds. So when you drop them 1 centimeter, you double the weight. So the 4 pounds goes to 8 pounds after 1 centimeter. After 1 centimeter, the 1 pound goes to 2 pounds.
What?
Then you go 4 pounds. Okay, you want to double the weight.
So you drop something 1 centimeter and it doubles its weight. I could probably test that.
You go 4 centimeters high. And then you go 16 centimeters high. And then you go 64 centimeters high. So you're always going 4 times higher. So 4 times, and the same thing's happening with the 4 pounds. So you double the weight to 8 pounds, then you double it again to 16 pounds at 4 centimeters, and then you're at 32 pounds.
Right, I am totally lost at what you're on about now.
16 centimeters. So at 16 centimeters, this 4 pounds will weigh 32 pounds. That'll be its impulse weight. And for the 1 pound...
So you're basically saying when it goes 4 times higher, it weighs 4 times as much. Interesting that.
To weigh 32, I'd have to go, 4 times 64. I mean 64 times, 16 times. Well, it doesn't
Do you have any idea what you're talking about here?
matter. You would just stop at 64. Why hurt my brain? It's 220, whatever. So,
Yeah, why hurt your brain? Numbers and adding shit together. Or subtracting seems to be a problem.
we just say that 64 inches is 4 times the 16. So if we do this 64 here, that's 4 times 16. All right, so at 16 centimeters, the 4 pounds is 32 pounds. At 64 centimeters.
What the hell are you going on about here?
The 2 pound is only 16 pounds. So it's 16 to 32. Clearly, the 1 mass only weighs half as much. Okay, when it's dropped from 4 times the height as the 4 mass.
So you're basically just seeing the evidence of what happens. And now you're just, again, drawing on a board and saying, this is how it is. Do you not see how ridiculous this is?
Okay, and so for the rest, I'll just play what I ended the other video with. But... And again, I'll just say, if you think your video is good enough, submit it as a paper, right? You would expect me, if I did the experiment, to submit it as a paper, right? That I'm going to do the experiment good enough.
No, I wouldn't expect you to do an experiment, actually.
That I could submit it to a journal, and they would accept it, because it's a perfectly, it's detailing something that hasn't been proven yet. So why don't you do...
It hasn't been proven yet. Again. Really?
If you think it's good science, submit it as a paper, as a proof. All right, so let's jump to the end of this video. where I explain gravity. Again. Okay, over and over. So we need this on. Come on. You can do it, computer. Thank you, computer. Alright, so maybe I'll just make that full screen, frankly. And make it all easier. And then I can just lift it up here, I think. And that should be close enough.
Wow.
Oh, yeah, I ought to do the funny part where the 4 pounds on the scale thing. It's the ridiculous part where they believe
you don't understand
such nonsense. Get rid of this. Alright, so this is the simple argument. And it goes back to the simple argument that, look, they really believe that if you take a scale, right, and you have two one-mass objects here,
Right, it's not about belief, it's about observation and what really happens.
Identical objects. You put one of them on, you have one energy. Okay.
Right, so what you're saying is if you put a mass on to a scale, it compresses. But what compresses it? You've got to think what's compressing it. So we've got a mass, and it's been accelerated down due to gravity. So it's its mass times its acceleration, which equals the force. So that's what's pressing it down. That's what's pushing the spring down. The force in newtons.
And you do the exact same action. You put the second one on, and now you have 4 energies. I mean, that's, it's so fucking stupid. You say, no.
Right, if you double the mass, the acceleration's the same, but you've doubled the mass. So therefore, it's twice the force, because it's mass times acceleration. That's the force. So if you double the force on a spring, it compresses twice as much, yeah?
Really believe that. So we're talking about. So they're really basically saying that 200 pounds is 4 times the energy of 100 pounds. So if I put 100 pounds on a scale and it has a certain amount of energy, they're saying all I have to do is put 200 pounds on the scale and have 4 times the energy. I mean, it's ridiculous.
No, it would compress the spring twice as much. Which, yes, if you took those weights off and released it, yes, it's compressed twice as much. So it took twice the force, and it's compressed twice the distance. So if you release it, you get 4 times the energy.
Ridiculous. 1 mass and a 4 mass. Okay, 4 mass, 1 foot, 1 mass, 4 feet. All right, the simple truth is this will fall in 1 second, let's say. Let's say we put it at the height that it falls in 1 second. So it's in the gravity 1 second, and it hits.
Yes.
It gets 9.8 velocity. It's in the gravity 1 second. It goes 4.9 distance. What happens here? Okay, 2 seconds is all it takes. 4 times the height, only 2 times the...
It was 2 seconds.
See, now, in his experiment, he could have shown us a couple of examples, pulled the camera back further, shown us a couple of examples of the objects just falling naturally, videotaped it, and
I did do that. I did it with the 1 mass and the 4 mass. Well, obviously the 1 mass is falling pretty much the entire length of the rod. And I also showed the 4 mass falling freely. Again, if you paid attention.
Just time it then. You could just time whether it was the 2 seconds. Because it's just an absolute fact that in gravity, it'll take 2 seconds.
I don't need to time it because the heights determine the velocities, which this bar's shown to a margin of error of 0.1
seconds for something to drop 4 times the distance. That's an absolute fact. So you know you have twice the velocity if it's exactly twice the time. If it's twice the time, it's twice the velocity.
Yeah. So, again, you're just reiterating if it's twice, well, half the time, or twice the time, however you want to say it. But yeah, if it's doing that, then it's going twice the velocity, which it is, isn't it? Because we verified that.
Velocity. So it goes 4.9 here. Okay, it goes 4.9 here. It goes 4.9 here. You know, these are all 4.9s. Okay. But what does it have in velocity? Well, it has 9.8 here. So here is 1/2 the velocity here. I mean, why can't they deal with this argument? It's an absolute fact. You're going to go half the velocity when you've only traveled 1/4 of the distance, the total distance. And you're already going half the velocity. So you have to understand that that second travel, you can't be collecting units of force for every unit of distance because you're only going to collect 9.8. In that much larger amount of distance, you're only going to add 9.8 to your velocity. You're not going to add any more than that. You're going to add 1 unit of velocity.
Yep.
And it's going to land with 19.6. So half the velocity is here.
So it's obviously not gaining the same as it gained here. In this 4.9, it got 9.8. And in this whole giant, what is that, 15? In this whole 15
Oh, that was
meters,
good off the top of your head.
it only got 9.8. So in this whole 15 meters, it only gained 9.8. That's all it gained, 9.8. 15 meters for 9.8. I mean, isn't it kind of obvious that there's no way?
So it got 9.8 in 4.9 meters, and then it got 9.8 in 15 meters. Again, it doesn't make any sense.
The one, okay, got,
It doesn't make any sense to you.
okay, 1 unit of energy here, and 1 unit of energy here, and 1 unit of energy here, and 1 unit of energy here. So it's 1 times 4. It's obviously only 1 times 2. 1 times the time, 2 seconds. 1 times the 2, and this is obviously 4 times 1.
So we're still using this. I mean, I did ask you this question because you argue MGH, MGT, but I asked you about the MG part because G is the gravitational acceleration. So what you're actually saying is mass times acceleration, which is equal to the force. So the the FMA, the thing that you just deny, you're actually, by arguing MGT, you're arguing for mass times acceleration. Dear.
So this has obviously got twice the energy that this has.
Twice the
to
weight.
tell you they have the same.
Twice the weight, twice the energy.
Right, again, twice the weight. Well, no, it's not, is it? Because you've just seen, I know it's probably blown your mind, but you've just seen real physical evidence that a mass that's 1/4 of the other one weighs the same. So it's not twice the weight, is it? It's 4 times.
Work any other way. 2 pounds is twice as heavy as 1 pound. It's twice the amount of work can be done with that much weight. You can't do 4 times.
Again, you've seen it.
Work. It's just silly.
Energy. It's just stupid. It's moronic. It's retarded.
Stupid, moronic, retarded. But at the end of the day, it's true, and you've seen it for yourself now.
It's fucking goddamn unreasonable. That's the word. It's unreasonable to think that in 2 seconds, even though it only got 19.6, even though it was going half the velocity here, okay, that somehow it collected 4 times the energy. And no, it didn't.
Right. But again, it did, didn't it? You've seen it.
Didn't happen, won't happen, can't happen. And that's why in 300 years, with all of physics' men, all their horses and all their men, they can't put this Humpty Dumpty lie together again. Okay? They can't go back in time and fool people.
Well, I haven't got, billions of pounds worth of scientific equipment. I just use my noggin. And there you go, it's proved, isn't it?
Because, well, they can, because obviously that's everybody's fool.
Yeah, so that's the joke. But the truth is that in 300 years, they haven't proven it because it can't be proven because it doesn't happen. And so go ahead.
Right, it does happen. It's well evidenced. It's well documented. Like, it's just ridiculous what you're claiming.
Publish your really ratty and crappy experiment, and I will counter-publish the critique that points out, look, the moron's too stupid to even use a spring that compresses more than a centimeter. So he's forcing a very deep...
Right, again, I've used softer springs, and I could use every spring in the world, and you deny it.
...detailed thing to be measured in a very small amount of space, where if he had done it with a less stiff spring, then the difference between a half and a full would have been
higher and lower spring constants,
centimeters instead of millimeters. And then if you're a little bit off, it don't gonna matter. So a millimeter off here, a millimeter off there won't make any difference, but it makes a big
it is about a millimeter off as predicted.
Difference when your entire compression of the spring is only 1 centimeter. So anyway, junk experiment, blah, blah.
So, not fake now, just junk and blah, blah, blah. Okay.
It's not my fault. It's not my bad that you're idiots, that you're fools and dupes.
Okay, that's probably enough. All right, so yeah, so I will concede I jumped a little too quickly. I didn't think about the fact that the velocities are constantly changing and that the average velocity I was showing.
Right, you didn't think. You tend to do that quite a lot. The velocities are constantly changing. That's because they're accelerating due to gravity.
Was unfair, and the only average velocity you can do is the velocity right near impact. But obviously when you start doing the velocity,
which in this video I pointed that out, that if you're going to do any analysis, that you've got to do it close to the point of impact. I did have a go myself. It wasn't perfect. Disc bars was fantastic, but the fact is I pointed this out and you still made this ridiculous mistake.
Right near impact, you start running into all kinds of frame rate problems because you're trying to do a tiny amount of distance.
Well, the frame rates don't seem to be a problem, do they?
And that usually doesn't work very well. So anyway, enough of the video.
Well, it did. It worked. It worked exceptionally well once this board did it.
Until the next time and such. So my apologies for the incorrect analysis, but the conclusion is the same.
So apologies for your incorrect analysis, but not for slandering everybody, calling me a fraud, a fake, which is, it's untrue, isn't it? That it's you could almost say it's slander or defamation of character, because what you said isn't true, and you were vile and nasty to others. So all you can apologise for is because you fucked up.
The video they produced was still a piece of shit.
Right, who's they? I did it in my living room at my table. I'm not a part of they. I'm just showing what happens.
And it's right there in the picture. Obviously, this spring is compressed more than this spring.
Yeah, you'd be correct in saying that. And like I say, all you're doing here is illustrating exactly what was predicted. So you haven't come up with some amazing thing here that I can debunk the whole experiment. And again, you still seem to be overlooking the major fact that this is a 1-to-4 ratio, and this one has twice the momentum. This one fell for twice the time, so it destroys your whole MGT argument as well, doesn't it? Because this only fell for twice the time. Yeah, it has 4 times the energy.
Obviously, and it's a few millimeters, 2, 3, 4, 2, 3 anyway. And
so 2, 3, 4, 5, 7, 9, just pick a number. It's about a mil, isn't it, really?
3 millimeters out of 10 millimeters is a lot. That's a lot of error. So it reads as if these two springs are compressed.
Not a lot of error at all. Exactly. Pretty much bang on. Speeds are almost bang on. Predictions on compressions almost bang on. So, no.
Exactly the same. The little thing is pointing right on the 3 line. They're both saying it's the same weight. Those two springs are not the same compression. Fact.
It is. It is a fact that they're not compressed the same. And like I say, what's the point you're making here? Because you're still missing the point.
Okay. Let's see if there's some other thing to measure it based on. Well, the 1 is the giveaway. Yeah, and like I said, I can't. Is my arrow here? See if my arrow is here. I could use my arrow, but it's not here. All right. Well, anyway, you can kind of see where the 1s are. You
I can kind of see how fucked up this is, and it's not in line or anything.
The other one is really close to the pink. That's how big a difference. That's how off it is. And the very fact that the 2 shows, and the 2 doesn't even show on the ruler in the other case, clearly one spring is more compressed than the other.
Yeah.
All right.
You're right.
Until the next time, and such, and so forth, and whatnot. Get rid of that. And... Oh, frozen screen. Great.
So yeah, in conclusion, not really, no apology there to anybody. Just a vague apology for you completely doing looks like, seems like. Still completely missing the point, still not following along, still not paying attention. So what else can be said, really? I mean, you need to watch and listen and take on board what's being presented to you. You're still not doing that. And like I say, now it's gone from, it's not fake anymore, it's just junk. But it was, I think this, you've gone to great length in this video not to sort of say, oh, it's fake. And then what have you titled it? Fake physics. So, not really an apology, you're just basically saying, oh, I messed up, which, yeah, you did. But, again, you just try and follow along. So I'll just add here at the end, obviously, with the frame rates being so good, I don't need the marker. I mentioned that in the comments. So a couple of nights ago, I did go to the trouble of setting it all up again, and did it without the marker on, which, you're just looking at the edge of what's falling now against the measurement of the backdrop. So I'll probably upload some of that, because it's slightly bit clearer, in the compressions. Obviously, the foremast compressing a little bit more, as predicted. But you'd have to follow along to understand that, wouldn't you? So, I'll get some of that together. After I've uploaded this one, obviously, I will upload that one. And Dispar again could maybe analyse it if he's so inclined, and we can see how consistent and how accurate this setup is, because it's kept very simple. There's not a lot going on really. Dispar's analysis showed that they were almost, for two separate runs of each, which it wasn't like I played one video and then played it again. They were actually separate runs. That's how consistent it is, because we're dealing with gravity, which is consistent. It's a constant. Obviously, we're not changing the masses, we're not changing the heights, so it's pretty repeatable. And now I don't have the problem of the marker getting in the way. Get nice clean drops every time. Takes all the laborious, painstaking, trying to get nice clean drops. I can just get them every time now, so I can just repeat. So there you go. I'll upload that when I get a chance, but I'll put this one up first, just as a response. I should at least defend myself against, lies and slander. But all I can say is, like I say, just watch the videos, follow along, take it on board before you jump in with both feet, because you made yourself look a fool, really. You jumped in with both feet, as it seems like, which you're dead against, and it's you seems to do it all the time. So, like I say, just watch the videos. I know you've watched them anyway. So, but watch. You have to watch them. You have to listen and take it on board, rather than just going, fast forwarding through and go, and not paying attention. This is where you go wrong. You need to pay attention a bit. There was also some mention of the camera being, $600, which it was nowhere near. And even if it was, if you've got $4,000 to offer somebody for an argument, then I'm sure you can spare $600 for a camera. But like I say, it was nowhere near that. But if anybody's interested, I'll make a separate video about the phone and what I used. All my previous footage on the other phone was 420 frames per second at 720p. The new phone can do 980 frames per second at 1080p. It can also do 1920 frames per second at 720p, and what I filmed in was 7560 frames per second at 720p. So given this frame rate, we can kind of understand how quickly these, you know, when it's dropped onto it, how quickly these things are happening and how high a frame rate we need to see these things happening. So if anybody's interested, I will make a video entirely about the device, how much they cost, where you can get them from, what model make it is. So there we go.